Welcome back, and we have the third lecture.
Thank you. Thank you. Yeah, thank you. So so I just finished this morning. As I was moving a little bit fast, just trying to get to the end of the deterministic part, I realized that I forgot to say a few things that are important. So let's get back to this theorem that you're looking to prove, the gravity waterways. Now, the concept here is that we have this modified scattering. Now, this turns out to be a pretty broad phenomenon for this type of equation. So, for example, for equations of the form, like the Schrodinger equation would be the typical one, I dt plus delta u is u times u squared. So for this kind of equations, this turns out this phenomenon of modified scattering turns out to be a pretty broad, that's the correct dynamics at infinity. This goes to, for example, this work, much more classical work of from the 90s of Hajnaumkin and Ozawa. I think Ozawa was probably did this early in the 90s. So there are, you could think of the waterway some kind of a more complicated version of this operator, in which we have, instead of having the delta, we have this fractional Laplacian, and instead of having the simple nonlinearity, you have a more complicated nonlinearity that comes from the waterways. And but the phenomenon at the end of the day, it's a similar phenomenon. And in fact, on the first paper that Fabio and I wrote, so for the first paper that we wrote, we looked at this model with a certain power of the Laplacian here, maybe minus delta. And we ran basically the same argument for this particular model. And that's how we developed that part, and then we put it together with the waterway. So it all goes combined. Now, one thing that I wanted to point out, because related to other lectures as well, is that it has to do with the correction. So the correction, I wrote it here explicit, this is the correction that one gets. It turns out, so the Hamiltonian structure is important here because the danger could be that the constant one gets here is not real valued. If one was looking at the wrong equation, then one would get the constant is not real valued. And if the constant is not real valued, then this would not be just a phase. It will increase, for example, and that will destroy the whole thing. So it's so there's something important about this formula, and it comes back, if you want, from the Hamiltonian structure. It's like if you were to look at the cubic NLS, this would be the good cubic NLS, but if one was to put an I here, then it would be a bad cubic NLS. One could do many things similarly, but not at the level of global regularity. So that's one thing that I wanted to bring up. Okay, so now we are moving. The last lecture, I'm going to be moving towards a topic that we understand much less. So the part that I discussed so far about deterministic solutions, that's something that I think by now we understand it pretty well, and we understand it for this model, we understand it for other models. Now, what I'm going to talk about in this last lecture is this topic that we understand much less, namely the wave turbulence theory for waterways. Ultimately, that's, at least in my mind, that's the primary goal of the wave turbulence theory, to understand the wave turbulence theory for waterways. And because it's connected, so it goes back to this, it's connected to this, to Hasselmann's theory. Now, we have, the theorems are much weaker in this case that we have. On the other hand, the picture that is developed so far is more like, okay, we don't know how to do waterways, but we can do simpler models. And the simpler models that are much better understood by now are the one simple model is much better. There are completely integrable models that work different, like the KdV equation, and the completely integrable models in one dimension work differently. But the equation that's been mostly understood so far is the semi-linear Schrodinger equation, which is exactly the equation that I had here. So it's the usual semi-linear wave Schrodinger equation, I dt plus delta u is equal to u squared. Now, in order to make it, it should not be integrable. So in order to do that, one has to look at this equation in higher dimensions, in dimensions d bigger or equal than 2. And that's work that started. A few years ago. There was work done before as well, but the more recent results are the ones that are more connected to our problem. So the results are these results of Buckmaster, Germain, Hani, and Chata, and Deng and Hani, Collot, Germain, and Transtafilani. There are various semilinear models that they have analyzed, and they proved they proved what's called the derivation, the rigorous derivation of the so-called wave kinetic equations. I'm going to discuss at the end of the lecture a non-rigorous derivation, like what does the kinetic equation, what does the wave kinetic equation have to do with the original system? So I'm going to give an example in which we can derive it, at least at the intuitive level. One can establish this as a goal to derive the wave kinetic equation. This can only be achieved if you control the solution long enough. The only way you can reach the wave kinetic equation is if you control the solution in the so-called kinetic time. We are nowhere close to being able to control the solution of the kinetic time for water waves. So the way I'm thinking about this problem and the way I'm going to present it is, we are looking at this problem. We are looking at randomized initial data. So the initial data is going to be randomized in the Fourier space. So you're thinking of random variables in the Fourier space with identically independent Gaussian distributions. And a simpler version of the problem would be to understand, like a simpler version one can state, without even talking about the wave kinetic theory, is to say, for randomized initial data, how long of a time of existence can we control the solution on? On how long of a time of existence can we say that the solution stays smooth and stays essentially randomized or almost randomized? So that's how I'm going to present the problem, because otherwise, given that we don't have any way to get the kinetic time, we cannot derive the equation rigorously. Now, the question is smallness. The central question is, what does smallness mean? So how is the solution small? And if it is to be relevant to the Hasselmann theory, smallness is a much weaker form of smallness than what we've seen before. So what we've seen before is smallness that's at the level of the L2 norm being small, or actually even more than that, like weighted L2 norms being small. The only thing that we can assume in our case, for today, is that the solution is small locally. So the local energy is small, or we can pretend that the L infinity, the number of derivatives doesn't matter. It's not about derivatives. So we can pretend that the L infinity norm is small, or the local energy norm is small. But of course, you're talking about oceans. So the total energy, the L2 norms, everything that's like L2 or things of this sort, these are giant. They cannot be used to measure the time of existence. So the smallness is the smallness parameter. That's something. So there's something to keep in mind throughout. The smallness is basically the norm of the solution in L infinity. So it's as long as you're talking about local norms, and as long as you think that the derivatives don't matter, it doesn't matter. I put L infinity here, or locally L2, or locally H10. So that's the analog. So the smallness is only in terms of L infinity norm, and that's what's relevant for the kinetic theory. Okay, so this is an introduction.
So you mentioned kinetic. So what would be the kinetic model that
So I'll get to it at the end. So we'll get to the kinetic. I'll derive the equation in form, not the rigorous derivation, the formal derivation of the equation. I'll do it at the end. If you want, this is what it is. To have a quick review, is this model here. So it's dt of psi. So psi is this energy. Psi is supposed to be the solution of the kinetic equation. And then we have a collision term. The collision term for the gravity capillary water waves. The collision term turns out to be the sum of 5 integrals. This is the simplest one. So this would be the simplest kinetic equation, in which we have psi is this energy distribution, and dt psi is equal to this a collision kernel in the sense that it's all quadratic. All of the terms here, they are quadratic. It's all quadratic. For this model, for the gravity capillary waves, and that's the form. And I'm going to describe how to derive it at the end, just to connect the theory. But for now, let's look at the frame. The way I want to think about it is I want to think without having to talk about the wave kinetic equation. I just want to think of the problem as being I have initial data. I know that the time t is equal to 0. We have initial data that's small in L infinity and it's randomized. On how long of a time of existence can we control the solution in such a way that we control the energy and we control some form of randomness of the equation. Okay, so let's talk first because it's simpler to write to write precisely the framework. It's easier. It's a little bit easier to write it for the cubic NLS because the equation is very explicit. Is the one that I wrote over there is IDT plus delta U is equal to U times absolute value of U squared. And the torus, so the problem is put on the torus, so it's the torus of radius L. And what do we want to measure? What we want to measure, so the object that's supposed to satisfy the kinetic wave equation is this energy. So it's the amplitude of the Fourier mode. So the U hat of Tk. We are in a finite volume, so K is going to be some kind of discrete lattice that has to do with the size of the torus. So so what we are talking about, the object psi that we are looking to find the equation for is this energy. So if you look at what does it depend on, this depends on time. At every time t we have so it depends on the time, and it also depends on the frequency k. And you should think of k as being originally k is in the dual of this lattice, so it will be multiples of 1 over n, integer multiples of 1 over n. One can also pass to the limit as L goes to infinity, so one has to let L go to infinity, and that will become a function on the Euclidean space. Okay, and what is the average taken over? So the average, the picture is the following. We start with initial data that's randomized. Now, if we look at the initial data, so this is the solution. Actually, this is not the initial data. The solution, this is in the Fourier space. So in the Fourier space is given by these coefficients U hat of Tk. And what do you assume about the coefficients? What we assume about the coefficients, the time t is equal to 0, prescribing the coefficients like prescribing the initial data. And what we assume is that they are of the form. So we have an amplitude that square root of this phi of k, which one should think of as basically some kind of Schwartz function. So I can think of phi of k or square root of phi of k as a Schwartz function. We have this normalization factor L. We have the normalization factor lambda in front, and this whole thing is normalized in such a way that the L infinity norm is equal to lambda. The L infinity norm of the generically is equal to lambda. Eventually, it will become epsilon, but for this discussion, the normalization is such a way that, and the eta, so of course the eta, these are random variables independent relative to all the frequencies. So for every frequency, you have a random variable, and they're independent and identically distributed random variables. So this is how the initial data is. The normalizations here, they're in such a way that basically the L infinite norm on average is lambda. So the L2 norm, if you want the L2 norm on average, so the L2 norm is lambda times L to the power d over 2 is proportional to the norm of U in L2. Okay, so that's so these are the basic normalization. One should think that L is a giant. So L is the giant number. Lambda and things like that, they are small, but L is much bigger than lambda. Okay, so that's this is the setup, and the average. So the average, of course, is taken over all the choices. So it's an average over omega, which is the space of the random variables. So that's how the average is. That's how we get this expectation, and that's how we measure the solution. And at the end of the day, we want to control this to establish an equation for this average. Okay, and in fact, so here I wrote it explicitly what it says. So what one wants to prove, there's also rescaling. So in order to be able to pass to the kinetic equation, one has to rescale. It turns out that for a cubic equation, so these equations are the nature of the equation is important. It's a cubic equation. For a cubic equation, if you think the time of existence, the natural time of existence, would be the size to the power -2. But because we have to take full advantage of the randomness, and we need to see so the full time of existence, assuming can take advantage of all the squared cancellation, everything that has to do with being random, and we need to do that in order to be able to hit the wave kinetic time, is lambda to the -4. So it's not lambda to the -2, it's lambda to the -4, coming from the fact that one has to understand fully the squared cancellation. And so the question, the wave kinetic theory for this equation, it goes to, so the question is, assume we are looking at its expectation, T kinetic, so this is a fixed number, T kinetic has to do with lambda, so it's lambda to the power -4. We rescale it, and then what we want to say is that the new variable is going to depend on the variable, so the kinetic time, the time tau, which is going to run from 0 to 1, then it has to be that this expectation is close and it approaches this function n, and the function n is going to be, the function n is supposed to solve a wave kinetic equation. And I didn't write it here explicitly. I have the way, so for this particular problem, it's a slightly simpler kinetic kernel, the collision kernel. But we are going to have a collision kernel in one of the water wave problems at the end. Okay, so that's the theory one would like to understand. There are multiple things one has to do. If you don't want to, at the simplest level, there are fewer things one needs to do at the simplest level. At the simplest level, one needs to show that one can extend the solution up to the time lambda to the -4. No matter what, you have to do that anyway. So you need to demonstrate the ability to use the random in such a way to extend the solution for such a long time. And of course, afterwards, there's more to prove. There's things that have to do with the wave kinetic equation to derive the whole theory. But that part is needed, and it's kind of like an independent part you need to be able to do anyway, to say that I have randomness, and because I have randomness, I'm able to extend the solution on a time that's much longer than what should have been if it wasn't for the randomness. So that's the analytical content of this. Now, you see, before you hit the kinetic time, the equation doesn't make sense because this tau. So because of the rescaling of the time. So if the time that we can hit is, let's say, lambda to the -2, which were like the earlier theorems. So the earlier theorems were more like the time would be more like lambda to the -2. Then the biggest value one can get here would be lambda squared, and lambda would be very small, so one wouldn't be able to take these limits. So there would be no equation. The only way you can get an equation, so you can get this non-trivial, non-linear increment, is by hitting the kinetic time. And if we go back to the references, so the picture that I had described earlier up to a shortened times, it was developed by Buckmaster, Germain, Hani, and Chata, and it was Deng and Hani who were able to hit the kinetic time for this particular equation. And in dimensions, in certain dimensions bigger or equal than 3, it turns out it's a little bit easier in higher dimensions. Okay, so that's the picture that one wants to establish, and we are going to focus only on establishing the regularity theory up to as long as we can. So the time is going to be more like how long of a time can we establish the regularity theory. Now, how do we do it? So how is it done in the Schrödinger case? In the Schrödinger case, one can expand. So one can start with the solution, and one can just put in So we can just think of the linear part of the solution, and if we just think of the linear part of the solution, then u would have would be equal to e to the I t delta phi, where phi is the initial data. So the first approximation is u is equal to e to the I t delta phi. Then afterwards, of course, there's the Duhamel term that comes by looking at the nonlinearity here. And then when we look at the Duhamel term, this is the Duhamel term written like that. Now we have to keep expanding. So u, afterwards you have to put the u's, the three u's that we have here, we have to put them all in terms of phi. Because in all of this theory, keep in mind the hardest part is to be able to use the randomness. So whatever the hard part is, I mean, these solutions, these formulas work all the time, but we don't know about these u's that they are random. So the only way we can use the randomness, or the only way we know how to use the randomness, I don't like it, but that's the reality, that the only way we know how to use the randomness is if we express the solution essentially as some kind of a point. It's almost like a polynomial, if you want, in terms of the initial data, because at the level of the initial data, we know that all the coefficients are random. So basically the picture would be, and I'm going to draw some graphs on how does one look at this formula. So the picture would be, we start with the linear theory, we start with the linear equation into the linear solution into the IT delta phi, and then we put them, so we put this u, so we put again this formula for each component u here. You can imagine at the cubic level, what we are going to see is e to the I, it's at the point s, it's e to the I s delta, and then it's another e to the I s delta, and then the u bar will contribute e to the minus I s delta. So that the cubic, so we're going to have a cubic term, and then we have the next order term, so we'll have a quintic term afterwards. And we have to do, so the whole expansion, and the reason why I have to do the whole expansion is that I said because the core information that we need to track is the randomness. And unfortunately, that's how we know to do it. When you look at it the first time, it looks, I mean, to me, it looked at the beginning, like maybe 5 years ago, it looked like this cannot be the right way, because you can expand, the solution can expand like this, but how are you going to see the Hamiltonian structure, things of this sort, how are you going to see them once you do this expansion? Every term at a time doesn't retain any of the structure. But unfortunately, all of that is less important than being able to track the randomness. And this turns out to be the right way to do it. One can expand this, one has these really long expansions. So just as a preview of what we need to do, we have these long expansions. We have cubic terms, then we have quintic terms, then we have septic terms, and so on. In some sense, you could say that they get smaller and smaller because there's some smallness in the problem, but they get smaller and smaller kind of slowly, and you get more and more of them. You get factorial more of them. Every time you expand, you're going to get more terms. There's some kind of polynomial decay because of the smallness in the best case scenario. So then afterwards, one has to organize these terms. So one ends up with this really long so-called Feynman diagram. So this would be the Duhamel formula, but when we keep iterating it, we get the so-called Feynman diagrams. And one has to organize these Feynman diagrams and get like the hard part of what Deng and Hani did is to organize and to understand what parts contribute more and what parts are negligible. So that's in a very simple, very naive point of view. But unfortunately, one has to do this whole thing. So we don't know how to track randomness unless except by doing this expansion. Okay, so that's a very quick, just a very quick description of what they do. It's kind of naive, but it's a simple description. Now let's see in our case. I'm not going to keep going with this. I'm going to move to our case because that's for the waterways. Yeah.
What is wave turbulence here in this result? How can I see the wave turbulence or the turbulence?
So the turbulence has to do with the fact that the energy modifies. So if you're able to hit up to time 1, the energy, so so this energy, pretend that it's equal to n. So the energy is going to be whatever is at time t is equal to 0 plus another cubic term. So it's the fact that it modifies the profile of the average energy on a unit time. Imagine this equation as dtn is equal to n cubed. Then n at time 1 would be equal to n at time 0 plus something that has to do, so it's more the energy profile changes. So that's where the turbulence comes in. And that counts as turbulence. So indeed, that's another question. Like, does that count as turbulence? It does. So that's, or at least for people who work in this, it counts as turbulence. The fact that you modify, you change the profile of the energy, you changed a little bit. So, I mean, still, this would be a well-posed equation on such a short period of time. So there's no blow up, there's nothing like that. No, not on such a short period of time, no. No, that would be much more of a dream, like trying to establish that there is some kind of growth of Sobolev norms. This is more like, once you think of the kinetic wave equation as being of the form like some kind of variant of dtn is equal to n cubed, and up to time t is equal to 1. If n is small, that's going to basically double. It's going to change the n a little bit, but that's and that ultimately changes the energy, and that's the answer to. It's a limit, somewhat of a limited answer. That's true. So there's no growth. There's no one cannot prove more than that. You don't get so far. Yes, afterwards the question becomes, let's study the wave kinetic equation. This is a Zakharov equation. I should have written it, but I wrote it the variant. This is actually the Zakharov equation. This dtn, exactly the one that corresponds to the cubic NLS, becomes some kind of resonant equation for the resonant kernel for the Schrödinger equation. All right, other questions? Yeah, one could think of doing more. One could think of trying to use, but of course that's very far. And in any case, for water, you are not able to hit the kinetic time, so there's no. We don't have a way to link it to the wave kinetic equation. Okay, so our goal. So that's what started a few years ago, and we started it. We had actually for several years we had what's called the Simons collaboration, and that was part of the goal of the Simons collaboration was to understand. For other models, they're also experimental things. So this was maybe like a small part of it, but for the math part, it was to understand. So the goal that we started back then was to understand this type of wave kinetic equation. So the derivation of the wave kinetic equation. This is called the rigorous derivation in the context of waterways. Now, the waterways, there's one core problem that changes the way you think about it, and a lot of other smaller problems. So let's start with the core problem, namely that this whole thing, this whole theory depends on understanding this formula. And this is the Duhamel formula. So it hinges on the fact that you have a description of the solution in terms of the nonlinearity. There's no loss of derivatives here. So because of that, the Duhamel formula basically describes the solution. And if you iterate the Duhamel formula, then you can hope that the errors will get smaller and smaller, assuming you can organize the whole thing very well. So that's the story, and that's what they're able to implement. They're able to implement this expansion of the Duhamel formula. Now, for our case, we have a problem right there because we have our equation is the water wave, and that's quasi-linear. So the Duhamel formula does not describe the solution. One can write the Duhamel formula, but when we do the first level Duhamel formula, we lose a derivative. We can recover the derivative if we're able to do energy estimates, but not if we keep doing the Duhamel formula. And in order to be able to do this expansion, one has to keep doing the Duhamel formula. So that becomes the first issue, which so far we haven't been able to get around it in a full way. We're able to get around it in a certain way, so able to still prove something, but that's a core difficulty. Namely, the Duhamel formula does not describe the solution at high frequency. One loses derivatives, and in fact, you see the issue is you lose the derivative in the first expansion, but then you have to keep expanding. So then we lose another derivative, and then there is no stop of that. And the more you expand, the more derivatives you lose, and there's no simple way to go around it. Okay, so this is the central problem. So we have our mechanism is the same. It's a similar kind of mechanism to what I tried to emphasize in my first two lectures, namely that we have two things we need to understand about waterways. We need to understand energy estimates. We need to understand something else. It's nothing to do with energy, which in that case was decay. In our case, we need to understand the propagation of randomness. So what we want to do, so the method we want to do, we want to establish these two steps. So we have to prove energy estimates. So this would cover the highest order of derivatives. And they are deterministic estimates. At this stage, you are not able, the highest order of derivatives, you are not able to take advantage of the randomness. The point is that we establish energy estimates, and then we look at what drives the energy. What drives the energy are the lower frequencies, the ones that come in into the bulk term. So those are the lower frequencies. So at the highest order of derivatives, we prove a deterministic estimate in which the bulk term is going to be essentially some kind of L infinity norm. Let's pretend to use we actually use the same quintic energy inequality. So we control the bulk term by the L infinity norm. The L infinity norm. That's how we control the increment of the bulk. And then on the second, so this is the first step. And the second step is instead of having a Z norm, we need to propagate the randomness. So the randomness, at that stage, we can think at that stage, the highest order of derivatives are accounted for by the energy estimate. So at that stage, we have to expand. So at that stage, you're able to expand the solution in the Duhamel formula. We lose derivatives, expand to a finite order. So everything has to be optimized. The exact numbers we have to optimize them in order to get the long time of existence. And so we have so we can expand up to a finite order, and assuming we can control, if we can prove randomness, eventually the L infinity norm. So the way we control the L infinity norm, we control it as by the L2 norm and the randomness. So we get a factor of the dimension to the power -1/2. So this is if we have control of the energy and we know that the solution is somewhat a certain type of randomness, that's how we can get the L infinity norm. Yeah.
Propagation of randomness, we need chaos propagation.
Yeah, propagation of chaos. Yeah, it's the same thing. Of course, the random is not propagated. So any nonlinear interaction, even up to time 1, because you have some nonlinear interactions, originally we have the very strong form of randomness. So you have this, every single mode is completely independent from every other mode, but once you start doing nonlinearities, there's no true anymore. So whatever propagation of randomness one has to make sense of that. It's not, so one has to make sense of what the propagation of randomness really means. And all of this, we should, so all of this, it's, we are going to have a law. So let me state the theorem such that to understand. Okay, so this is the theorem that we have. So this is a theorem that, it's a theorem with Fabio and Yu Deng that we proved about a couple of years ago. So we are looking at we are looking at the parameter alpha, and we are assuming that R, so basically we're assuming that R, epsilon is this number, the L infinity norm. Epsilon is the number that measures the L infinity norm. This is the one that we know to be small. So you're looking at solutions of amplitude epsilon, and R has to be sufficiently large. So these are so R has to be sufficiently large. Like R would be, one can think that R is large relative to epsilon. And then the claim is that with probability almost probability 1, so almost e to the probability almost 1. We can control the solution on a time of existence, and the time of existence we can get is epsilon to -8/3. So the time is epsilon to -8/3. If we were to be able to, this is the best time we can get. What one would like to do is to get the time of existence epsilon to -4. If we are to compare with the cubic NLS, the only way to see the wave kinetic equation is by hitting the time epsilon to the -4. So the time that we get here is smaller For a while we thought we can get epsilon to -3, and it turned out there was one of these chains of interactions that was a little bit worse, so we were able to get epsilon to -8/3. Okay, so that's the, yeah. Did you have questions? Okay, so I'm going to describe some of the elements of the proof. As you see, it's not the other theorems that I talked about earlier. The deterministic theorems are essentially definitive theorems that one cannot really do much better, other than changing some parameters. One cannot do much better here. One could, in principle, imagine that what we have here is a certain mechanism, but the time is obviously not what we would have liked. So the time goes to epsilon to -8/3. But of course, this is also the first result for the water waves, and we have to account for these difficulties that do with the loss of derivatives. Okay, so what I explained here is that the randomization. So the randomization is basically a Khinchin inequality. If you have a function with random coefficients, then the L2 norm and the L infinite norm, they're almost equivalent. And when we do this on a big domain, then it turns out that we gain a factor of the size of the domain to the power -1/2. The L infinite norm is smaller; it's about of the size of the L2 norm times a coefficient of. So A is the size of the L2 norm, which is big, but the L infinite norm is R to the power -1/2 times A. It's consistent with the mass being uniformly distributed on the torus. If the amplitude is epsilon, then the energy would be epsilon times R to the power 1/2. If the function was to be uniformly distributed. Okay, so the main issue, as I say, as I explained a few times, is that to propagate this randomness using the Feynman diagrams and combine. So we have these two steps in which we combine the energy estimates, and then we use the Feynman. We understand the randomness. Okay, so I'm going to describe now. Of course, the energy estimates I already described them. So the energy estimates are deterministic. So those are essentially those we know how to prove essentially ideal energy estimates in the deterministic case. We use the quintic energy inequality because that's the best we have for this problem. I'm going to describe now how do we do the second part? How do we propagate the randomness? And the way to do it, what you'd like to say. So remember we had something like Q of t is equal to e to the IT delta was there. In this case, it's our dispersion relation lambda times phi plus some kind of an integral from 0 to t e to the IT minus s lambda times some form of u squared, some kind of cubic interaction. So we want to do the expansion in this way. This is essentially what we need to do. And now, because we have, in order to be able to run this argument, we cut the nonlinearity in several ways. So we cut the nonlinearity at the level of how many terms do we have. Now, that's the cubic term. But the water wave equation has more than cubic coefficients. It actually starts from quadratic coefficients and cubic and quartic and so on. We have a bunch of terms. This n are here. So I wrote a little bit schematically how we do it because otherwise the formulas are too complicated to write. So schematically, we essentially expand the solution up to, let's say, r terms. We're going to see exactly how to normalize things. And they also cut them in frequency. So we cut them in frequency we truncate them in frequency with these little Palais projections. Now, at the expense of what? The point is that the high frequencies, we are looking for a finite time of existence. The high frequencies, we are going to control those just with the energy, because so we can control them with the energy, and as long as these parameters are set sufficiently large, like this, the frequency of the cutoff is sufficiently high, the remainder is going to be small enough relative to what we're aiming for. Okay, so we think of the equation, this truncated variable, in which we simply solve just the problem with finitely many copies of the function in the nonlinearity and up to a finite frequency. And the rest is going to be an error that comes from the energy estimate. And then, so the truncation has to do with it's basically a small power of the domain. And then we do the initial data. So this is the problem. It turns out that, actually, I think I have a pretty concrete statement here. It turns out that if we can control this equation, this is a self-contained equation. If you think, assuming that here we take, let's say, 10 terms, the 10 terms in the expansion, and assuming we cut the frequency, this is basically a self-contained equation in which we prescribe data and we have to evolve. So then we have a statement that says that it's basically what I was saying, that the higher order frequencies and the higher order nonlinearity contributes less just because we have control of the energy. And we have room to lose. So if we could have done all of this perfectly without this kind of losses, they've hit epsilon to the -4. But because we have all of these losses and we have room to lose, we have to perform this cutoff. So what it says is that after this first step, so this is the concrete proposition. It actually doesn't have all the hypotheses because it would have been too hard to write all the hypotheses, but it basically says that as long as we control the truncated version, we can control the true solution with essentially without any losses. Okay, so now what we are looking to do is to understand this equation, and we want to understand. So we want to understand it on a shorter time of existence. I also assume that we had already done the normal form. It turns out it's not so trivial. So to do the first normal form, it's not such a trivial part. But let's just focus on this part of the equation. So what we have now is an equation in which there are no more loss of derivatives because basically we use the frequency projections to cut the frequencies, and here we have a few terms in the nonlinearity, and I'm going to compare this mainly because it would be too complicated to write. I'm going to compare this with what we know already, namely we know how to understand the NLS. So if we just look at them, this equation, let's pretend we could prove whatever we want about the cubic NLS. How do we, not whatever we want, let's pretend we can prove whatever is true about the cubic NLS. Then how do we pass to the water wave? And I'm going to think of this as the simplified water wave. Okay, so let's compare these things. R to a small power. R has to be R to a small power.
You have T sub R.
I'm sorry? So this is RTR. So RTR, the truncation is capital R. Think of capital R as the biggest parameter. But we have many derivatives. Our energy is the level of lots of derivatives. So the frequencies above R to the power 1 over m, those are very small when we measure them in any norm other than the highest number of derivatives. So that's why those contribute very little, in fact. So we think, let's say we think m is equal to 10, and then this means that the frequencies are cut at size r to the power 1 over 10, with the understanding the high order energy is going to be, let's say, the energy age 100.
And the small r stands for what?
So there's a number r here that how many terms, so we think of cubic, quartic, quintic, and so on. And we stop at, let's say, r is equal to 10, with the understanding that the remainders, they are going to be, so you stop at a, and the remainders are going to be less because they carry more copies, basically.
So this is after doing like 10 line.
Yes. No, I'm sorry. This is the nonlinearity. So we just think we are not at the level of the Feynman expression. We just think here we have a nonlinearity. This was not exactly cubic in our problem. In our problem, we had the long expansion. Now, okay, so that's an important point. There's a big difference between a polynomial of the function and some kind of another combination of the function, because the randomness is preserved for polynomials, basically, but not for exponentials or other things. So that's why we need to think of this nonlinearity as being some kind of a polynomial.
One other thing, the exponent minus 8/3, it is just the last bit with respect to epsilon minus 3 that you have given for the normal form before.
Epsilon minus 3, if we didn't have any loss in this part, and for a while we thought we had no loss, we'd have gotten epsilon minus 3, coming from the fact that we had the quintic energy inequality.
Yes.
So the quintic energy inequality would have given us at best epsilon minus 3 because there were 3 copies of L infinity. And unfortunately, lose another little bit in one of these chains. It turns out there's a certain chain of interaction.
But in the previous talk, you showed us that if the radius, if the torus R is large enough, you have a deterministic theory for larger times.
Yes, but the norm is very important. So the norm that was small was the L2 norm.
Okay.
In our case, the L2 norm, so the energy norm is giant. We cannot use it. The smallness has to be described in terms of epsilon, and epsilon is just the L infinity norm.
That you control in epsilon minus 3.
Yes, so it's only the L infinity norm that's small. In some sense, the whole difficulty of this whole it took some time to understand. So basically, the earlier work on it took some time to understand that unless you prove some theory in which the only thing that's small is the L infinity norm, then it just has nothing to do with the wave turbulence. You don't get to the same problem. So if we wanna understand, if our goal is if we want to understand the Hasselmann theory, then it has to be that the only norm that's small is the L infinity norm, and it's the natural picture in the ocean. So the L infinity norm is the local size of the waves. They are small, but it's a big ocean, so you cannot. There's no smallness at the level of the energies. So everything has to, that's the only smallness in the problem. Okay, so now I'm going to describe a few slides of how do we look at this equation, assuming we have this other, assuming we have the right theory for this other equation, and how do we, at the end of the day, the question is how do you organize this graph? So you have these long expansions, they're finite, we are going to do all of these expansions are going to be finite, we are going to stop at some point, but still we need to organize it pretty well to get any time. Okay, so basically so how do we, so the first, I have a few thoughts. Now the loss of derivative is, the loss of derivative has to do with where we did this cutoff. Because you can pretend that here there was another derivative, let's say this is an extra derivative than the linear part, because this is how the waterways are, but that derivative is trumped by the cutoff. So because of this, there are small losses of derivative that have to do with R. So as long as so basically what this says is that basically what I mean to say is that even though the problem we need to look at all the higher order nonlinearities, it's really the cubic one that plays that we need to understand the cubic one. If we understand that one, then eventually the others are not getting harder. So you need to understand the cubic nonlinearity. So then this means that we are getting closer to this model here. Okay, now the next thing has to do with counting resonances. So how do we look at this problem? So when we look at this problem, as I said, we start with this kind of formula, and let's say that we're already at the level at which we just got at the cubic level, and then we have to plug them in. So basically, we are going to plug in every single one. So here's a frequency C. At the frequency C, we have, so we start forming the graph. So the graph comes, so we have 3 frequencies here that are going to determine the frequency C. And it could be, so there are the 3 frequencies. So when we expand, of course, we have the first one also, but when we expand, we are going to have e to the is lambda times phi. So we have 3 frequencies. So every frequency C is decomposed as a sum, and they all sum to the frequency C. So this is, so at the first level, the solution is one can describe in terms of these ternary graphs in which every frequency C is decomposed as a sum of 3 frequencies that are, so the sum of the 3 frequencies that come in is the frequency C. Now one of them also comes with the bar, so one has to keep that in mind. And then the way we think of the solution is at every stage. So these are the frequency C. So let's say this is C1, C2, C3, C4. So C2, afterwards, you have to plug this in terms of its own expansion. So you have to expand. So expand all of these frequencies. So we have this kind of picture in terms of the graphs of the solution at the frequency C is being, now the advantage that when we do this expansion, all that we see here is the function phi. Like for example, for the cubic level, so if we were to be at the first level, this would be the frequency, some frequency of function phi, which is what we wanted because it's for those that we had the randomness. So the disadvantage is you have to do these long expansions. The advantage is that at the end, so let's say we expand. Let's say we expand it up to some point. At the end, we only see the function phi. Or it could have been like maybe this one didn't have to expand because we could have put in this term. So then this can also stop. So this at most will have will have an expansion up to how many you want to expand, but it can also stop if we put in exactly the linear solution in one of the terms. Okay, so this is basically how our solution is going to look. It's going to look a superposition. So this is going to be a sum. So the solution at the frequency C is going to be, you see here is going to be a sum because every frequency can be decomposed as C1 plus C2 plus C3. So this frequency C is C2 plus C3 plus C4. But then we also have to take the sum over all these possible frequencies. So we're going to have a giant sum. We can imagine how this works. At every frequency C, the cubic level is the first expansion level. It's easy to see because we just expand each one of them, but we have to take all the sum. And then what are we looking to estimate? We are looking to estimate them. We need to track the randomness. We are looking to estimate the energy of this T and C. So let's say K. So the energy. So this means that we have to estimate the U of dk squared, and we have to take so is the expectation of that. Okay, so how do we do this expectation? Well, we think that U of dk, the absolute value, it's a positive quantity. The absolute value is U of dk times U of dk bar. So this means that we have to look. So U is a sum of all of these Feynman diagrams. These are called the Feynman diagrams. Once we keep expanding them, we get the Feynman diagrams. Let's say it's a finite sum. Let's say we stop at some level, and then we have to multiply by the bar, which means that we have to look at U of dc times U of dc bar. So then this means that we have to pair the frequency. So this C is going to be paired with the complex conjugate. And if we look at the expansion of the complex conjugate, we're also going to get an expansion of this type. Let's say we're going to have terms of this type, like each one of them is expanded. And then at the next stage is where the squared cancellation happens. Because all that we have here are functions. So this is going to be phi, let's say, at some. So it's going to be the original function phi at some frequency, and then phi at some other frequency, and then so on. And then we have to do the same thing with the bars, but these are the phis now. And the phis, they are independent. Every frequency is completely independent from all the other frequencies. If we integrate over the space, over the measure space, the space of Fourier coefficients, then we get 0 unless we get squares. So the square root cancellation means that basically here we are going to have lots of frequencies, but when we pair them with the corresponding frequency from U bar, it's only the square root. So all of them have to be pairing with something else. So if we are to draw the picture, because it's only at the level of picture. So we have, let's say these are the bars. The terms that survive, let's say you're expanding up to the second order, the only terms that survive when we do these sums are the ones that are paired. So for example, this one would be paired with something here. They don't have to be paired. And then this other one would be paired with something here. And then the third one would be paired with some other term here. And you have lots of possible pairings. You see already we have, you can start imagining it. You have lots of possible pairings, but the only ones that survive are square root of them, because originally, let's say we had n of them. We had n, n components. So this would be, but they have to match. So each one of them at the end, in order to survive in the average, has to match against another one that comes at the end. So it's only, so you have much fewer frequencies than, it's not, the sum doesn't take place over all the possible decompositions, but only over the decompositions that match. Okay, very good. So now this means that, so this is where you take advantage of the square root cancellation. Now, we are also going to have all these integrals. And it becomes, understanding the size of these integrals has to do with there are no more times in this. So once we expand, and let's say we put them in terms of the functions phi, we can integrate the phases, all the integrals that come in, and there are lots of them. So this would be the first level, but then when we put the u itself, we are going to have second level integrals, and they're going to have lots of integrals. And we have to integrate all the times. Then there's no more time dependence, and those are going to become coefficients. They basically depend just on the frequencies. And what do we want to say? We want to say that this is what this is what I have here. The coefficients that come in are coefficients that come in here. So this will be lambda is square root of c. So this is going to be some kind of square root of c, and then it's going to be square root some other frequency, and then square root some other frequency, and we have to add them all up. And it's a counting problem. So the question is, so the most basic level, the most basic counting problem. Assume I have a bunch of frequencies c that are, let's say, discrete. How likely is it that this whole sum, and we are going to get lots of sums like that, is in an interval, is in a given interval AB? And this is a non-trivial problem, because basically the frequencies that we are looking at are frequencies of the form integer divided by L. So there's a number theory problem there. Now, if we think of it discretized this way, then the question is, for what kind of, let's say we have integers between 1 and capital N, how is it possible for this kind of sums with this kind of integers to be in a given interval of a certain length? And that's a non-trivial problem, because like it's a number theory problem. How do we know that discrete the sum like of this form is in a given integral in a given interval? And it turns out that we can do. The way to think about that is that if this interval is long enough, then being in an interval, it doesn't matter that the frequencies themselves, they are integers. As long as the interval is long enough, it's as long as all of this would be a set, as long as all of the diameters in every one of these variables is bigger than 1, the number of integer solutions of such an equation is proportional to the volume of the set. The volumes are not hard to calculate. What's hard to calculate is the number of integer solutions in a set, in a thin set. This turns out could be pretty thin, and it turns out that that's not the time. So in order for that to be an easy number theory problem, we arranged that the time is much smaller than r, which means that these frequencies are spaced. There's a small spacing between them, as if we are looking at as if we ignore the fact that they are supposed to be integers. Okay, so that's part of the restriction. So at the end of the day, this is one of the restrictions that we had in the original theorem, namely that r has to be larger than this epsilon to the minus 8/3.
I guess this is a phase, right?
Yes, this is going to be equal to this phase. This is going to be equal to this phase, and then it becomes a denominator when I integrate the times.
Yeah. So you can 0 or non-zero.
Yes, but it turns out it doesn't help you. So it's not any easier to put in a different interval than around 0, and it's actually more complicated because these are at different times. So in order to so the complete problem, the robust problem you have to solve anyway, is to look at all of these squares of all of these lambdas of the frequencies and measure that in every interval, not just around 0. It makes no difference around 0. It doesn't help you. You just want to say that it has the proportionate number relative to the size of the set, the correct proportion. You cannot do better than that. So you cannot do better than that. These are many of them. It's not like you have 2 or 3 of them to be able to say more. You have a lot of them. Okay, so that's now. Okay, so I'm going to move a little bit faster through this. It turns out that there's a certain renormalization that's important. Namely the cubic terms. It turns out that the trivial resonances, they would contribute too much to be able to bound them. One has to use the fact that the Hamiltonian structure in order to eliminate them using a phase. Okay, so that's something that one needs to do even for the cubic NLS. Now, in our case, the question is how to do that. This is basically how they come in. This is how these cubic interactions come in. If the equation was a simple equation, so it was like the cubic NLS, then when we add up over the K1s here, we get exactly the L2 norm. And the L2 norm, thankfully, is conserved. So the renormalization factor is basically doesn't depend on the frequency, doesn't depend on the time, because it's the L2 norm. In our case, it's not true anymore. So in our case, we are going to have the natural renormalization, the natural analog of the renormalization would have to depend on the solution itself. And for a while, we didn't know. So on one hand, you can renormalize it depending on the solution. And that's good, that looks good for a while, but you lose at the very end because the renormalization is going to depend on the solution. But then all this pairing doesn't work out anymore because the randomness is expressed in terms of the polynomials. It's only the polynomials that if we have exponentials like that, then the pairing doesn't have to be at the end. So the only way to renormalize it to keep this pairing that I was described earlier is to have a renormalization that doesn't depend on every solution at a time. It's an average renormalization. It's going to be not as good of a renormalization, and that's what we end up doing. So we have to define this other function gamma in order to be able to track that. And okay, so there's one more issue, namely that it's kind of a technical issue, namely that I wrote the equation, the cubic equation, but the equation originally was quadratic, and we can do the first normal form, but the randomness has to be the graphs themselves that one gets. If we think that the randomness happens at the level of the initial solution, then the randomness of this gauge solution is not going to be ideal. So one has to account for that. What we end up doing is we end up with working with this kind of graphs, but at every stage we allow another expansion in potentially two parts. So we have 2 types of nodes. We have these basic nodes, and we have another kind of nodes that describes the normal form nodes. And at the end of the day, the working dimension 1 is what leads to the time of epsilon to the minus 8/3. Because there are certain, we have to organize all of these graphs, and it turns out there are certain chains of interactions that are worse and which add up in a way that leads to the time epsilon to the minus 8/3. Okay, so I'm not gonna. It turns out that being in dimension 1 is actually a disadvantage in this case, compared to dimension 2 or dimension 3, because of the small sets. Okay, so that's the way I see it is the first result is kind of a partial result. We didn't quite get all that we wanted, and I'm going to summarize here the conclusions that what we learned out of it. So first, it's still a wide open problem. It's substantially more difficult than in the case of semi-linear terms because you have to design some kind of an argument that accounts for the loss of derivatives, which is what I say here, that the dual formula cannot be used. Now, the way I think of time as existence is because we are not able to hit the kinetic time. So I think of it as a proxy for. So I think of the time of existence as a proxy for wave turbulence. Not hitting the kinetic time means that we don't derive the wave kinetic equation. So I think of it as a proxy. It has the advantage that it's easy to compare. So if if one can do longer time of existence, in principle, is a better result. So it's easy to compare the time of existence if it's easy to compare theorems in terms of the time of existence. There's also this other issue that I didn't talk about it because it's a subtle issue. Like, what does it mean to take the square of the Fourier coefficients? We can do the Fourier coefficients. There are various ways to do it, and none of them is clearly better than the others. We can do the Fourier coefficients of the variable after the normal form. We could have done it for the variable before the normal form. Or we could do, instead of having exactly u hat of c squared, maybe we could have done some other bilinear operator of u hat of c that has the size of u hat of c squared, but is not exactly the same thing. And these all subtle choices. We don't know exactly what would be the right choice. And in any case, measuring things in terms of time of existence, we bypass this kind of issue. So that's some of the things we learned. What we also learned is that the model you looked at is probably one of the hardest models. We thought of the gravity water waves as being the simplest model to think about. It turns out it's probably one of the harder models. And I want to describe, just in the last 10 minutes, I want to go through what is the kinetic wave equation? How do you calculate the kinetic wave equation out of a model? So if we start with the model, how do you calculate the kinetic wave equation? It turns out that for the gravity water wave, it's a little hard because it's a cubic equation. So I have the calculation here done for the gravity capillary water wave model in one dimension as well. It's the same equation I had earlier in my lectures. So dt phi, it's only the difference only at the level of phi. Dt phi, this is the gravity term, and then I put back this capillary term, and then the rest is the same. So it turns out that this is already a better equation. It's a better equation because it's actually quadratic. For a quadratic equation, you're only looking for the kinetic theory takes place at time epsilon to the -2 as opposed to epsilon to the -4. And the equation itself, the wave kinetic equation, it's easier to derive. So I'm going to describe this as the last, the last part of my lecture. I'm going to describe what's involved in derivation of the wave kinetic equation. So with some of the things we know, we already know some of the things. So G, we have two parameters, G and sigma. They are both 1, and it turns out that they are both 1, and the dispersion relation becomes square root of absolute value of c plus absolute value of c cubed. This is the dispersion relation for the gravity capillary waves. The diagonalized variable is almost the same as we had before, except that for h we have to put the identity minus the Laplacian to the power 1/2 h. So that's the correct variable that respects the Hamiltonian structure. So then once we do this normalization, the equation that we get is dt plus I lambda u. It's a sum of three nonlinearities, and the nonlinearities, this is a nonlinearity of u plus and u plus. So u and u, this is u bar, and this is u bar u bar. And in principle, we get all of them. In this problem, we get all of them. Okay, so these are the quadratic nonlinearities, and they are defined by symbols, so m plus plus, m plus minus, and so on. And they are defined by these faces. The signs over here, iota 1 and iota 2, they have to do with whether we are looking at the variable or the complex conjugate of the variable. Okay, so this is the equation that we want to derive. It's a formal derivation. It's not a mathematical derivation. It's more, you're going to see. You might not even believe it once you see it, because I do some approximations that are not. Okay, so you'll see how the equations are. One does this thing for any model. Any model, like this would be for quadratic. For any cubic model, one can do a similar calculation. Okay, so we start with the initial data. So this is the initial data. U hat at time 0 is b of t. So b of t is a given function, and this is the expressions of g of c omega. These are the the independent complex Gaussians, and we are looking at this function psi. So the equation is going to be for the function psi. The function psi is going to be a positive function, and we want to derive the equation. And we are given, so there are certainly normalizations that have to do with these parameters. And how do we approximate? So the A, this is the first approximation. The A, so the solution, I forgot to write it. So we move to the Fourier space, and the solution after we move to the Fourier space is given by, so u hat of tic c is equal to A of tic c. So A of tic c is equal to, the first approximation, this is the UML formula, is B of C, the initial data, 1 over 2 pi r is a normalization factor, and then we have these symbols that are coming from the nonlinearity, we have the faces, and we have the quadratic terms coming from the solution itself. So this is the first level, and then we feed the solution back into itself, and at every time we do the expansion, so at every time we have, so A is going to end up with a B plus a quadratic part, so A squared is a quadratic part, plus a cubic part. Turns out that we can stop at the cubic part. You can do a full expansion, but just for the non-rigorous derivation, we can stop at the quadratic part, at the cubic part. So it's B, A2, and A cubed. The second ones are easy to compute, because in the second ones, what we put here, we put B's, and when we put B's, they don't depend on the time, so we can integrate this. The only dependence of time happens in the phase, so then the phase becomes a denominator, and we integrate exactly in time. So the A2, there are 3 of them, the corresponding the signs, and they're easy to compute, and they carry the phase in the denominator as we expect it, coming from the fact to integrate in time. Okay, so this is A2. And now once we have A2, we can put we can calculate the A3. So the A3 means that we take again this expression, so it's B, we had B, and then we put the A2, so we have various combinations. So here we have B plus A2 on this component, inside the component have another B plus A2, and we have to carry out all of the contributions. And the A2s, they have various signs. So you have a few terms of this type that we have to carry out. And we get a bunch of terms. So there are symbols, multiplication of symbols, faces. Then we integrate another time. There's another time variable to have to integrate, so we get more denominators at different places. And at the end of the day, the cubic term is going to be something of this form. It's going to be B times B times B at different frequencies times this kind of multipliers that. So there will be multipliers that now pick up the faces and pick up the previous multipliers. They pick up the signs. So they are going to be complicated. Okay, and now we can do the pairing. It turns out that not all of the terms contribute, and that only some of the terms actually contribute. But now we can do the pairing. So there are 2 types of pairings that come in when we do the quadratic term. So when we do the calculated psi. So psi is the so there are 2 types of pairings. There are the pairings of A2 with A2 or of B with A3, and they're also higher order pairings, but they don't contribute at the level of the quadratic kernel. So we have 2 types of pairings, and let's say, for example, for the ones that come from A2 and A2. So if you look at what A2 is. Okay, so we have this sum, and then we have to pair this frequency eta rho with the corresponding frequency when we put the A2 of tic c bar. And they're going to have minus eta minus rho, and there are various, the pairing has to do, meaning that basically you only get squares. The frequencies that contribute in the energy are only when one eta rho is equal to the other eta rho of the other variable. So that's how we do the pairing at the level of eta2 squared, and then we also have to pair the B with the third with the cubic term. Okay, so we do all of these pairings, and it turns out that when we integrate, and I wrote here in order to have, when we have this kind of faces, whatever this face is here, it's e to the it minus 1 divided by the same quantity that becomes a sine squared. So what we end up after all these pairings, we get things of that carry the squares, and the squares are expressed in terms of the psi's. And we have various expressions of this type, and the only one that survive that are of this type that are sine of t times some kind of a phase divided by the phase squared. So this expression e to the ix minus 1, it turns out that the sine square comes from the fact that all of these phases, they were of the form e to the ix minus 1 divided by x. When we square them because we pair them, this becomes 4 sine of x over 2 squared. Okay, and now the punchline. So when we take the limit, as t goes to infinity, we have this limit. So the limit is sine of t times whatever, sine squared of t times whatever divided by the whatever squared is basically the delta function at the whatever. So then when we do this and we remove, there are lots of terms, so it's only the top order term that is we have to keep. That's why we end up with a relatively simple equation. We only keep the top order term. And we end up with a kinetic wave equation when we do this limit. And here I'm writing the kinetic wave equation. This is the result that we get. Turns out this is the simplest kinetic wave equation for waterways. There are only 5 terms that are left because basically one of the manifolds. So when we do this delta, these delta functions, we are looking at the manifolds that correspond to the phases. It turns out that one of them is trivial. When all the signs are positive, where all the functions have the same sign, then there is no contribution there. So you only have 2 manifolds with 2 corresponding signs. And this is the equation that we get. It's all. So if we look at it, it's not easy to understand it. They're all of the terms. So let's just look at one term. It's basically some kind of a multiplier. These are all positive multipliers. The way I wrote them, I put the sign outside. They're all positive. They're all real multipliers. That's important. And they're all of this type. So we are looking at the resonant manifold. There are two resonant manifolds, like C minus rho rho, or C plus rho xi rho. So we have to integrate over 2 resonant manifolds, and then we have here some kind of psi squares. So this is the wave kinetic equation, and so we have these two resonant manifolds. As I explained here, one of them corresponds to a trivial contribution that we don't need to record, and then here we have to restrict. So here we have to restrict this. We have to restrict. So the delta node, they basically say that we integrate over this resonant manifolds. And now it turns out these are not easy to understand even at the local level. So even at the level, is this equation well posed locally in time? Let's say we start with nice initial data. Is it well posed locally in time? And that's not easy to understand. And I want to just say a couple of words about that. That's not known for the water wave equations. There are only a couple of results. They're not. So these are the results that we are working on. The signs, which I have them all here, they are very important. And the symbols are real. Okay, that's easy to see the symbols are real, but the signs are also very important. And the reason why the signs are important for 2 reasons. If we want to preserve the positivity of the function psi, and to preserve the positivity of the function psi, it has to be that the first 2 signs are positive, because it's dt psi, some kind of psi squared. And if it was dt psi squared is good, but if it was dt psi is minus psi squared, then that wouldn't preserve the positivity of the function psi. So the signs there are important. What's more important is the negative sign, which counts as nonlinear dissipation in the 3rd term. So it's only the signs in the first 3 terms, they are important. The first 2 contribute to the fact that the function psi stays positive. The last one has to do with the fact that so you see this basically comes, this pops out in front. The equation is of the form dt psi is equal to psi times something negative in order for it to decrease. So what's important is this nonlinear dissipation, the dt psi is equal to psi times some other, let's say, coefficient a. But in order for this not to blow up, it has to be that a is negative, and that's the content of this 3rd term here. The other 2 matter less, but this one is the one that matters. That here we have psi at the point, so this is a positive quantity. the corresponding symbol is positive, and the sign is minus in front. So there are things that are subtle, but basically what I mean to say is even the local well-posedness theory for these systems is pretty subtle because it depends on identifying what drives the evolution. And so here I describe the two basic things that drive this kind of evolutions. For the gravity, the reason why I wrote it for the gravity capillary problem is for the gravity capillary problem, it's enough we can think of it as a quadratic equation. So the collision term is quadratic. If we were to do it for the gravity equation, it'd be a much longer calculation because you have to end up putting the cubic terms here. And then the cubic term means that we have to look at a lot more in the expression in order to get the cubic terms. So that's, but I think this is a pretty clear how to do these calculations. Thank you.
Go from the sum to the integral for the wave kinetic equation. Yeah. I remember that there is a number theory argument to have a good dimension here to go to the integral. Is the same for water waves or not?
So this is not a rigorous derivation. So yes, at the level of the
but it's for you for water waves.
For the rigorous derivation, I don't know.
Okay.
In the non-rigorous derivation, we just pass to the integral and we put a factor of 1 over r. There are various factors of 1 over r that come around here. Okay. It's like when you integrate. So for the non-rigorous derivation, yes, we kind of just don't do. We just put we replace the sum with the integral divided by r.
Yes. And second question, I missed something about your cutoff in frequency. How do you at the far end associate your toy model with a frequency cutoff to the real water wave, so which is quasi-linear?
Yes. Okay. So I can explain. There's this proposition I had here. Yes, it's actually not very. I don't have the whole hypothesis because there's been too much to state. How do you think about it? Why is it doesn't matter? Well, so what we are looking to do is, let's say we want to control up to 10 derivatives of the full problem. Now, the energy estimate will give us 20 derivatives, assuming we can close. And then because we control the 20 derivatives, but with the big factor in front. But as long as we cut away, so the high frequency, because we control 20 derivatives, the high frequencies, we can control 10 derivatives of the high frequencies, we divide by the corresponding power. Imagine like this, let's say we control the H20 norm and with the bound is 1,000,000, then the H10 norm, as long as we cut away the big frequencies, the bound we can make it very small. So this is the mechanism. We say we control the H20 norm with a big constant, but then the H10 norm, once we restrict to big frequencies, the H10 norm was much smaller because we gained the corresponding factor. So this is the game that we play in order to say that we can basically reduce to this kind of model.
Yes, and last question here, you stop at a number of wave interaction to big A.
Yes.
It's because you want a Gaussian hypercontractivity theorem, something like that at the end?
Yes, yes,
okay.
yes. The whole thing is based on the fact that you need that at the end. All of this square root cancellation, all of this is because you need to close. All of this has to be polynomials in order to close at the end.
Okay. And
so we need to stop. We cannot expand the fraction. So a fraction, even a fraction, if it was like 1 over, and there are fractions in the nonlinearity, we have to expand those because everything has to be a polynomial in order to be able to say that we have that we can preserve the randomness. Yeah, so there's an element there that it takes a little bit of work. This is an exponential. Yes, it's the hyperconductivity. Yes.
One question probably you said, but I've missed. You take the gravity capillary water waves because for gravity capillary you will certainly reach the kinetic time because we have almost global existence.
we hope that for gravity capillary waterways in 1D, so it's there's no global existence, but we hope that we can reach the kinetic time for several reasons. One of them being the fact that the equation is quadratic, so the kinetic time is epsilon to the -2.
But not only because if you choose the surface tension, you will have.
So maybe you have global
Because,
existence for small initial data, but not small in. So for the same is the same issue that. Yes, there is some advantage to the gravity capillary problem. That also has to do with the fact the problem is not truly quasi-linear anymore. So there's some advantage to that.
So at the end, you did the derivation of the wave kinetic energy through like this expansion of the function. Would it be possible to do it in a way that you can kind of see the Hamiltonian structure, at least formally?
I don't know how to do that. So here the expansion is basically we kind of stop. No, I don't know how to do that. That's so what we think is that our solution is this formula that we want to implement. A is b plus quadratic plus cubic, and then once we stop at the cubic, of course we don't see the rest of the Hamiltonian structure, and then it's only the up to the cubic that generate the quadratic term in the collision kernel. So we stop here, we stop at the cubic level, and already to get them explicit, you see, at the end of the day, we need to understand what those symbols are. It cannot be like no matter what we get is going to work the same way. That's not true. So if we were to have too many terms, then I don't know if we had been able to get it.
Any more comments? Yes.
One last question. So you mentioned there is a problem of well-posedness of the kinetic equation, right? But in your results, so you had the expectation of the Fourier mode squared minus the solution to the kinetic equation. So
yes.
you assume a priori it exists, or
for the Zakharov equation, the ones so what I had there was for the cubic analysis. For that one is known. Okay. For the kernel, for the kernel, the collision kernel, for the wave kinetic equation associated with the cubic analysis, that's known. Well-posedness is known. It doesn't have the issues that this one has.
But for your result, so you assume a priori that.
No, for our result, we need to prove that this equation is well-posed, and that's work that Fabio and I've been. Okay. It's not trivial to prove, and it's actually not known for any other. It's not known for any of the other associated kinetic equations. You can write them formally, but whether they are well-posed or not, it's not known. There's actually a very recent result of some people who did some kind of well-posedness theory for the gravity problem, and there are some issues that need to be understood, even at the level of the well-posedness of the kinetic wave equation.
Well, thank you very much, Alex, for this.
Thank you. Thank you. Thank you.
Right. And then it will be funny to continue.